Yeah, good afternoon. Yeah, first of all, thanks to Jack Roux to organize this wonderful meeting in this very nice place in France. I'm very much enjoying that. I have to loud up because getting older. So my talk today is just shown here, long-term behavior of heat production. Okay, let me start from this just a slide. For me, study on the anomalous heat effect is a very nice subject to pursue for more than years. Anomalous large heat generation phenomena have been manifested by various methods in various metals, as already we know. Especially recently, binary composite nanometals, including nickel, are found to be very effective. We want to explore the energy source. To do that, it is necessary to understand the uniqueness of a system and the commonality with other systems. We have conducted anomalous heat effect study by radiant calorimetry for nanostructures composite metal thin films with hydrogen or deuterium gas. Today, here, I want to introduce an example in which measurements were repeated over a long period of time using one sample. Okay, here's our experimental procedure. First, we have to measure the background. That is done before introducing hydrogen gas. That is corresponding to the condition of without hydrogen. And the condition of the temperature heat is something around 800 K to 1100 K. And the pressure that is just in vacuum, but less than 10 to minus 5 Pascal. And in this condition, radiation spectra measured at various voltage of heat. And then we move to the excessive measurement cycle. This one, let's see. I need a pointer over here. Oh, yeah, I got this. Okay, so this is just a heat measurement cycle. This is just one day cycle. In the night, we let the sample to absorb the hydrogen. It's done by hydrogen pressure about let's say kilopascal, and the heat temperature is something under 500 K, and need a time for 15 hours. Then in the morning, evacuate chamber, and together with the heat voltage raise up. And then the sample is heated up. Then start to the radiation measurement at various V heat, and in this condition. Therefore, we can measure the photon spectra. This should be including anomalous heat effect. And then after 5 o'clock p.m., we stop measuring and move to the next cycle. These are the one cycle measurement, and during the weekdays we do that. And after that, in the weekend, we do the continuous measurement. That is just for 3 or 4 days. Stay at the same heat voltage and without refilling the hydrogen. That's the one. Yeah, this is just sample of ours, and we have 2 samples just on the heater. This is a ceramic heater. Then this is set in the vacuum. So therefore, first sample filled with hydrogen gas, and heating and evacuating, then it makes excess energy. The measuring condition temperature is around 1000 K, and the pressure is also less than 10 to minus 5 Pascal. This is almost isolated in the vacuum. Therefore, the produced heat flow is carried away almost by radiation photons. So radiation power spectra, we got many information, not many, but anyhow, we know the surface temperature and also the emissivity of the sample. Now, it's a photon detectors. We use the three types of detectors, one mid-infrared region, and then near-infrared region, and optical to UV region. We are putting these things here, here, and these are connected, FTIR and ordinary visible light. This is splitted by these two analyzers. And also, we don't have so much money. I just put one system over here. And each measurement, we switched it to this place. So then the photon coming from here, we measure the mid-IR region by this detector, and the others by this detector, or something like that. This is a photo adjuster for that. So what kind of spectra we see? Okay, this is a typical spectra. Typical means very good one. And you see that we see quickly the difference between with hydrogen and without hydrogen. The black cross, the measured one, and the red and blue one is measured with hydrogen, I mean, during the desorption time. So, first of all, the spectra can be interpreted by gray body radiation. That's very good, because we can use this equation, just putting the emissivity over here. And then we can deduce the value of emissivity and the surface temperature. That's very good. So this is the kind of, this is a result of analysis for this system. You see, we can measure temperature. I mean, this is surface temperature and the emissivity of the surface. You see, during gas desorption, surface temperature increases a little bit, about 3%, and in this typical case, and the emissivity decreases, let's say, about 5%. And the radiation power from the sample, yeah, this can fit very well. So you can use just this equation, using the emissivity and the Stefan Boltzmann constant and the surface temperature to the fourth. So this is all obviously increases, because even without this calculation, you see that this increase of a total radiation power. And almost, I would say, again, almost no difference between H2 and D2. So how to evaluate this from the measurement for the excess power? So this is a simplified picture of our system. And the sample is heated up, and the radiation from the sample is denoted by QS. And also this, when the sample is heated up, of course, holder is also heated up. So we have a radiation from holder, which we didn't measure. But anyhow, we can estimate it. We can determine from the calibration curve, and very small amount of conduction heat flow from this to the upper flange. And also we have a reflection of radiation from the wall of a chamber. But this is very small, so we can neglect it. Anyway, if heat flows in steady state, then we can put this formula very quickly. In this case, we neglected QC. But anyhow, this is important. Then the Q total can be represented by QS. This is a measured one, by just putting the constant alpha. And alpha only depends on emissivity of a surface. So anyhow, therefore, calibration curve, you can obtain the calibration curve in vacuum by changing PE and determine the alpha, this alpha. However, if something happened, I mean, when the hydrogen introduced to the chamber, the surface might be reduced. I mean, the oxide things may be reduced. Then this emissivity changed, usually reduced. So therefore, we have to take in account in this effect. So that is done by this equation. So this is the final evaluation curve for this our measurement. So measurement was done, as I said, measurements were repeated many times for one sample. Today's case, nickel 1 Cu3 sample. This is just 6 layers of nickel 6 nanometer thickness, copper 18 nanometer thickness on just a nickel substrate. First background measurements for a week, that is without hydrogen. And second, the next measurement with hydrogen for 3 weeks, we call it H2 first. And then measurement with D2 for 3 weeks, we call it just D2. And measurement with hydrogen second time for 3 weeks. And during the weekend, we take a data, long-term measurement. Okay, so this is the evaluated excess power versus elapsed time. This is the excess power in watt, and this is time hour. And this is the various conditions just for the heater voltage, 38 volt, 40 volt, 42 volt. So that when you increase the voltage, I mean, this corresponding to the increase of input power a little bit, and then the excess energy, excess power increases also. But for the dependence of a time, I mean, this excess power stays almost constant in several hours, I would say. And seems to me that it increases. Just this is the first, this is the second, but deuteron, and third, going to this way, the repeating the measurement, and then the excess power is also increasing. And for this case, I calculate the generated energy reaches to 43 watt hour. And this is just corresponding to the 155 kilojoule for first 10 hours. Okay, how about the long term? Okay, this is the result of a weekend 80-hour measurement. This is taken by 10 seconds each point corresponding to 10 seconds, just get by mid-IR detector. So first, H2 first case, yeah, this is the first one for the long term, second one, 3, 4, 5, 6, 7. Okay? And then you see that this is the excess power. They are very fluctuating, but maybe slowly decreasing, but from here almost constant. And the next time, a little bit increased, and just decrease for the being in this region, but almost stay constant. And then so on, so on. So I would say, in this case, QEX increases by repeating absorption and desorption. And also, the QEX fluctuates very much for the being in the being, but became stable and very stable. And also, I would say the excess power persists for a long time, much longer than 80 hours, because we don't have data, but I cannot imagine it drops quickly. And also, even when this is constant, very stable, sometimes sudden radiation reduction occurs. And I calculate the generated energy for this one because in this case, initial storage quantity of hydrogen is just 6 times 10 to minus 6 mole. And I calculated, so therefore in this case, it is at least 410 keV per H atom. This is just using the assumption the whole initial value is exhausted as a fuel of this reaction. But hydrogen in the sample falls below 10% within 30 minutes. Then this should be more than 4.1 MeV. So this is the graph shows the just averaged excess power versus number of times gas absorption and desorption. So from the first, second, third, gas desorbed, and gas absorbed and dissolved, and so on. So there's three data here. For this circle one is just a one-day measurement, and this for squares one is just for weekend long-term measurement. Anyhow, it is looking at this, we can say that the QEX increases by repeating absorption and desorption. That is one of the interesting observation. And we also measure the excess heat power versus amount of hydrogen absorption. So this is the power versus absorbed initial absorbed value of hydrogen. So if look at this, then we can say easily as the amount of initial H2 increases, then the excess power increases very slightly. But if you apply this equation, the constant term is very large compared to the proportional term. So therefore, even it increases a little bit, contribution of the proportional term is very small. And also, this is the amount of hydrogen absorption versus times of repetition of absorption, desorption. So this repetition number increases the initial absorbed quantity of hydrogen seems to decrease. So therefore, even though the initial amount of hydrogen gas decreases, but it increases, we have increased QEX, increased excess power. So therefore, I just simply interpret this, the effect of repetition may be an extension of the region where the unknown reaction can occur. That's one point. And then the long-term heat generation continues without refueling. This is the first week measurement. This is 7th week measurement. Both of them continues very long without refilling the hydrogen. Okay, so as I said, amount of hydrogen in the sample decays exponentially, I guess, but excess power stays almost constant for more than 80 hours. How come? Amount of hydrogen in the sample at 3 hours later, it will be less than 10 to minus 6 times the initial value. That means for this case, only 6.10 to minus 12 mole for this case. And for this case, 5.1 10 to the minus 10 mole. Well, it's very small value. And I just wondering. And then just calculate the amount of outgas. That is mainly water, H2O and H2 from the wall of the chamber. And then I know that outgas is contribute to the 1.3 times 10 to minus 11 for this case. For H2O, and 1.3 times 10 to the minus 12 more for hydrogen. So this is almost same order hydrogen in the sample. So therefore, one of the thinking of mine is H2O and H2 collide with a sample surface very frequently because it's a thermal motion. And then calculate the number of the collision is just 8 times 10 to the 14 times per second. So thus, the effect of H2O and H2 gas, outgas from the chamber wall may not be ignored. And then also I compare how much energy can be produced from the very simple-minded reaction for the proton case. So I guess I don't have so much time.
You have about 4 more minutes.
4 minutes, okay. So I just say that in this case, 4p plus E minus reaction gave the largest thermal energy from this. So this is a kind of Feynman diagram for protons coming some of place here, and we need at least one electron, and then make a helium-3 proton in this. The curve. This is the energy removed by neutrino, because in this reaction always emits a neutrino. So neutrino carried almost all the energy of this reaction. So anyhow, I calculate this, in this case, just a 200 keV per proton. Thank you. The thermal energy expected from multi-phonon reaction at most 200 keV per H. The thermal energy from observation at least 410 keV per atom, H atom, or probably I would say more than 4.1 MeV. So what's the difference? Elementary reaction energy production is still mysterious. And I just skip this discussion because I almost running out my time. So therefore, I just show you our near future experiment. So we started this kind of experimental setup. We have 3 kind of detectors, but we are now introduced to this big spectrometer, Fourier transform IR spectrometer. The purpose of this to extend the measure region to much lower side, and in this device we can measure the far infrared region 0.006 electron volt to 0.08 electron volt, and mid-IR region 0.0747 electron volt to 1.23 electron volt. You see, this is just a first glance. It's not the real measurement, just a training for this, and we got this raw data down to, in this case, maybe 0.05 electron volt. And this is the spectrum measured by present system. You see, we don't have a make a combined spectra. Just get the whole region, and then we are expecting in this region there might be a connection between the high energy source production and going to the thermalized region. Okay, this is summary. We have shown the result of measurements on the same sample over a long period of time. The following are found in a series of measurements with a copper-nickel composite thin film during desorption of hydrogen. Excess thermal power increases by repeating absorption and desorption. Radiation power fluctuates very much at the beginning but becomes stable as the number of repetitions increase. Excess thermal power persists for a long time, much longer than 48, or 80 hours. Amount of produced energy per atom is much larger than 400 keV per hydrogen atom, but it may be more than 4.1 MeV hydrogen atom. So thank you very much.
We have time for one very quick question. Francesco, you had your hand up first.
Thanks. So at the first transparency, the composition nickel copper is 1 to 3, but before you used 7 to 1. There is some explanation?
Well, we changed the ratio from 3 to 1, 1 to 1, 1 to 3, and 0 and 0. And first we saw the copper 0 to nickel 3 to copper 1. It's greatly enhanced. And then we saw the 1 to 1 decrease a little bit. And then we saw the 1 to 3, and then it increased again. And then see copper go down again. So my opinion in this stage, it's important to need two kind of metals. Just one is not good. But the ratio makes a big change or not. It is still questionable, and we need a more, because it's it's not always the excess power. Excess power is not always exactly reproduced. Therefore, it's just experimental error within the experimental error, I would say now.
Okay.
Thanks very
Thank
much.
you.
Important.
Dr. Kasagi-san. Thank you
Thank you very
much.
much.